sustainable engineering and first robotics. This partnership has provided us a valuable 6 weeks experience, and we are so grateful for this opportunity. During this program, we improve our technical know-how, teamwork, and project management skills. With the knowledge we've gained here, we will apply them in the future to excel in our career and make a positive impact in our fields. Special thanks go to our program organizer Priyanka, whose support was invaluable. We also would like to acknowledge our client Laurie and Deirdre from Brigham and Women Hospital for their encouragement and feedback. Thank you to our robotics team Liger Boss 277 and our mentors Coach Gear and Coach Sean for their guidance. With all that included, let's cut into today's presentation.
Again, thank you all for joining us today. So in early July this year, Lori and Deirdre came to us with a problem. Right as it stands, currently there is no formal training for nurses to learn to detect hematomas in the femoral region after a catheterization procedure. And currently what they are using to teach and demonstrate the feel of a hematoma is a golf ball under a stress ball. So they asked us to help create a model that can better represent what a hematoma feels like, to help the nurses learn to identify and treat these hematomas. So the first step within our process was creating a project timeline. The first phase we have is deciding on the design. So this really meant creating a design that met at least the basic requirements of the project, which we'll go over in the next slide, and creating the project within a $500 budget and on a 7-week timeline. The second phase was material testing. One of the most important parts of this project was creating the correct feel of the hematoma and of the skin. So we had to play around with what materials to use and what would be cost effective. The third phase was prototyping, and after prototyping, having Lori and Deirdre feel the actual materials and feel like how the hematoma felt under the skin to ensure accuracy. And after that, we finally built our final project, which is displayed here in front of you. So the most important parts of this project were these 3 requirements. The first one being appropriate tissue pliability. This means accurately simulating how the skin feels. The second is simulated tissue pliability, which basically means accurately simulating how the hematoma feels under the skin. And the third is simulating a hematoma that is the size and feel of a golf ball. So for those of you who don't know what a hematoma feels like, it has around the pressure of a golf ball. And so we actually, for the third one, we actually created a hematoma that not only allows us to get the pressure of a golf ball and the size of a golf ball, it is a dynamic hematoma that allows us to have multiple sizes at the correct pressure.
With all these criteria in mind, this was our solution. We have a realistic skin texture which can be marked with an expo marker and then erased later. We have programming control and electronics that can detect correct pressure and give feedback via these LEDs. You can easily replace for any broken parts by taking the 2 parts at half. And then you can mechanically change the shape and size of the hematoma via this pump system. And then going into depth, you can see the inside of the model. Can you move the camera, please? Like to get it out of the way of the top right. Move it to the bottom left.
Okay. Oh.
Your other left, yeah, there you go.
Okay, so here you can see the inside of the model, which is just the structure of the actual silicone, and you can see the back side of the bone model. We started, as Isabella said, with the actual feel of the body. So we tried different materials. We found that an outer layer of dragon skin with an inner layer of silicone with foam in between gave us a good feel of an actual human body. And then, so we put that first layer of dragon skin to get the outer texture of the skin. And then we started attaching fake, mock electronics and devices to the bone, and then we suspended that within the model that you can see over there to pour the silicone into. So then then we pour the silicone, and then we could remove the bone after that. That gave us all the space to put the actual electronics in. We attached the electronics to the bone with Velcro We placed that in, we carved out some space, and then we carved out some extra space, put some extra filler for some discrepancies. And then we basically had 2 force sensors go into the electrical box where the Arduino microcontroller takes the input of how much force is being applied, and if it's the correct amount of force, it gives an output to the LEDs to give to the end user to tell them that it's being done correctly.
As Jake explained earlier, our mechanical and electronic components work together to provide an interactive and educational experience, which I will now demonstrate. So the first step to using this model is to flip the top silicone layer off of the bottom support. And then we need to turn the switch here to on so that the sensors can sense the force on the sensors. So I will take the bone off first. As you can see here, there are sensors on the back side of the bone, so that they can sense pressure when people press down on the model. Next, I will insert the hematoma, which is just a bunch of water bubbles. So I'll first connect it to the spike pump here so that it can inflate. When using this model, the closer the hematoma is to the surface of the silicone, the more realistic the feel of the hematoma will be. So I will put it right here under all the layers of foam and dragon skin. Okay, next I will choose where I want to put the pressure sensors on the bone. And I think that this is a pretty good location, so I will reinsert the bone back in the model. Okay, the next step is to put this back over here. Okay, as you can see here, there are 2 LED lights which will show me if I'm pressing on the right pressure sensors with the right amount of force. So I will first inflate the hematoma by pumping it up. Okay, as you can see here, there's a visible bump on the surface of the model, and when you press it, it is pretty harsh, just like a real hematoma. Now I can press around it, and when I press on the right sensors, the lights will light up. There's a chance that the switch got turned off when we flipped the model over, so I will turn it back to on.
Oh, there it goes.
There it goes.
Okay,
There
now
we
it's
go.
on.
Yep.
So that's the.
And you're holding it the right way. Your fingers.
There's another light on the top part.
Yep.
And Lulu, the reason we have one on top versus one on the bottom
Right.
is?
So, sometimes to stop more blood from flowing to the hematoma, the nurses need to press on the artery and the vein so that they stop the blood flow. And these pressure points are where they should press on. So that's why we put the pressure sensors there.
Awesome.
And then, yeah, as you can see, the pressure sensor got the pressure.
And that's what we look like. It's a lot of pressure.
It's a lot.
That's accurate.
So to release the gas in this hematoma, simply unscrew this part from the top. I'll take the top completely off and flip the silicone model over and flip the switch off. And that is how to turn it off. It's not off. Probably got turned back on. Now it's off.
So for our hardware and software part, we used an Arduino Uno microcontroller to control the sensors and the LEDs to program them to have the correct amount of pressure needed to be applied to light up the LEDs. These are all culminate into one electrical box that houses both the Arduino and a bunch of wires. All the wires. Here's the electrical without its shell, and all the wires were soldered straight on into the Arduino, which allowed it to be more stable and stronger. These wires come out of a small chute on the side of the box and go under the bone where the sensors are attached by Velcro. The wires are routed through special channels in the silicone, which lead the lights onto the back or the front, and the wires onto the bone.
And finally, we have the materials list and cost. So the materials we used for the model include silicone, dragon skin, food coloring, and sponge, and this is what gave it the actual feel of the skin, of fat tissue. We also used red and blue tubing to simulate the arteries and the veins. As for the hematoma, as we said before, it is a bunch of water balloons, about 10, 15 water balloons together on a bike pump, nose pump thingy. Sorry, I forgot the word for it. And then we also have a bone, which is a hip joint teaching model that we found on Amazon that has Velcro on it that allows you to move the sensors around. And finally, the electrical box is wood and a hinge. The electronics include 2 sensors, light bulbs, switches, wiring, Arduino Uno, battery, and Velcro. And finally, the support stand right there uses NGX insulating sheath and cloth. The entire process, including prototyping, testing out materials, that all came out to about $487.59, whereas this model itself comes out to a total of $326.08, which is significantly cheaper than other models on the market, which can range, other teaching models, which can range up to thousands of dollars. So these are some extra resources. We have a user manual, a website, and our project plan, which gives more information on our final project.
With that conclude, thank you everyone again for their contribution in this initiative, and feel free to ask any question about our project. We would like to share more details with you.